final project for recommendation systems, CSC 577. Um, our project uses implicit ratings to recommend news articles. Um, so our not only are our ratings implicit, they're also unary. So what that means is basically we're dealing with click, no click data to recommend news articles. This is very different from what we've used within previous learnings in class, which use explicit rating scales like 5-star rating scales. Um, Usually on the internet, the more common use case is unary implicit. So this is kind of exciting for us. And because it is different from the rest of the work that we've done in class, it does require a different set of algorithms, and therefore this is an algorithm-based project. We'll be implementing a multi-layer feed-forward network that will be trained on the user history and be utilized to create a table showing recommendations highest to lowest. Um, but in order to understand how good our algorithm implementation is, we do need to create a couple baselines. But like I said before, the surprise package, or more so, I said that we worked with explicit ratings. The surprise package, however, only works with explicit ratings. Therefore, we need to use a different package. We decided to use LensKit. So here's LensKit Home. Um, and here you'll see that it does implement implicit feedback or algorithms for implicit feedback. It makes it really nice out of the box. Here, all you have to do is set a flag for feedback set to implicit, right? So we used a KNN item based algorithm in order to baseline our algorithm against. And again, because this is news articles, we decided to create a content-based TF-IDF algorithm with cosine similarity as our distance measure. So the data set is the MIND data set, the Microsoft News data set. It comes with behavior and news. So just showing you all where it is. Here, it's very easy to download. All you have to do is agree. We actually ended up using the MIND small data set, which is a random sampling of 50,000 users and their behavior logs. And it's actually, the nice thing about it is there was a workshop where they had a leaderboard, which helps us baseline as well. We get to see how well we did against the people that were in the workshop, which is nice and helpful. So more about the data set. It includes click events, impression logs. So at the moment of an impression, a user is shown a certain amount of articles, and whether they click or don't click, that is their rating, right? But even so, the data set is huge, even if we use the small data set, right? So we ended up only using the impressions data, which is click, no click. More of that is in the notebook. But yeah, just a little bit of exploratory analysis here. Our final data set ended up consisting of 2 million rows, even though we did take a sample size of the small version of the data set. So again, it's a huge data set, and no need to use the whole thing for this class project. So here you'll see that the data set comes with a history. This is the user click history before somebody ended up looking at a particular news article, and the rating represents whether they clicked or did not click. There's also a news text data set, which basically just ties a news ID to a text of the news article as well as the category. You'll see that the rating distribution is really sparse, or I guess you could say that it's really imbalanced, where most of the users do not click on articles, right? It makes sense when you think about the realisticness of it. When you're given a set of articles, you only click a small amount of them. And then here's the news category distribution. You'll see that sports and news, interestingly, take up the majority of articles. Now, just to talk a little bit more about the algorithm, we use a Keras implementation for deep learning. This is essentially a content-based recommender because we use doc-to-vec embeddings. which I think was the big key here. It was a big step above the TF-IDF content recommender. Doctivec, if you're unfamiliar, it essentially takes into account um, the context within for a word. So it gives a word vector for every single word, and then we have to aggregate those down for every article, and then we again have to aggregate those down for every user, right? So we take those Doctivec embeddings for each user, and we feed it into our multi-layer feed-forward network to give us a personalized user history, right? So very similar to the TF-IDF, except we end up using the Doctivec embeddings instead of TF-IDF scores and things like that. So you can read this implementation details here, but I think it'd just be a little easier in the video if I just show what the recommender actually looks like, or the network actually looks like. So after getting our Doctivec embeddings, we have 4 dense layers, and we start out wide, go small, at 128, and then go smaller, 64, 32, 16. So because we start at 128, our input shape is 128, and that's the size of Doctivec embeddings we end up using, right? So in between every dense layer, there's a dropout layer, which just helps with regularization and things like that. Our output layer is one-dimensional, and we of course use a sigmoid function because it's click, no click, very similar to classification, right? We end up using the atom optimizer. Our loss is cross entropy, binary cross entropy, just for training and things like that. But of course, we end up using different metrics for our recommendation system. So a little bit about the actual metrics. We of course wanted to use precision at 5 and precision at 10, things like that. Recall at 5, recall at 10. But we wanted to also look at NDCG. The reason is because it was used during the workshop for the Microsoft News dataset. So that way we can at least benchmark against the people that were within this workshop, right? So without further ado, these are our metrics. Our metrics again are precision at 5, recall at 5, precision at 10, recall at 10, NDGC at 5, NDCC at 10, and again, just to compare back again, baseline against the workshop participants. So our item KNN does not do too bad. Of course, maybe in the context of class or with smaller data sets, more controlled data sets, this looks bad, but when you look at the NDGCs, 13 and 15, and the 306th ranked participant at the Mind Challenge has an NDGC at 5 at 21. This isn't terrible. Just keep in mind that this is just our baseline model. We did very minimal hyperparameter tuning. We just tuned the number of neighbors. We ended up going with 40 neighbors for the KNN. But again, it's just our baseline, so we were okay with that. VTF IDF content recommendation is absolutely terrible. It kind of showed how sparse the data set was in terms of usage of clicks and things like that. So it wasn't something that we felt like would have been a good algorithm, but we wanted to see, since we're doing a content-based recommendation system anyway, using the Doctivec plus feed-forward network implementation, we wanted to see what TF-IDF would look like, and it was bad. But luckily, the algorithm that we did implement, the Doctivec plus the feed-forward network, did really well. Our precision at 5 is 67, recall at 5 is 60, precision at 10 is 63, recall at 10 is 64, and our NDGC scores are really, really good. Again, I want to point out that we did use a small subset of the small version of the training data. So that said, even though we did a lot better than the people on the Mind Challenge's leaderboard, we want to point out we used a very small subset of the data. So I wouldn't say that we're out here, changing the game. It's more so that, we picked a small subset. And yeah, that is pretty much our project. One thing is we did do some sample balancing. Because of the rating column distribution, we used a near miss from the IMB Learn package. And yeah, but other than that, that pretty much sums up our project. Thank you.